Okay, we're going to continue on here, chapter 11. So in chapter 11, after we started talking about, we're going to be talking about really sort of the idea of electrons and where they are in the atom, electron configuration. And again, as we talked about early on here, sort of as electrons transition from different energy levels, again, they have to gain some energy to do that, which is endothermic. Energy coming into the atom to excite those electrons to a higher energy level, much like what you did with the flame test. When you obviously put it into the flame, it gained a lot of energy, those atoms, which excited the electron. Same thing happens when we do have electrons on higher energy levels. They really do want to kind of work their way back down to lower energy levels. And that is going to result in really energy being given off in the form of a photon of light. And that's an exothermic sort of process. As those guys drop back down in terms of energy, the atom has to release that same amount of energy that's required to do that. That photon of light and how energy sort of travels through space is in the form of waves. And waves basically have a couple of different sort of parts, as we talked about. There's the wavelength, which is lambda, which is really the distance between two peaks or two troughs. There's also the frequency, which is how many times a wave sort of passes a particular point in a second. The frequency has units of hertz, or reciprocal seconds, and they're basically a one-to-one relationship between those. A hertz is a reciprocal second. So again, you can just kind of change the units if you do come across something like that. The amplitude is kind of the distance from the midline to the peak of the wave. We saw sort of an equation that relates the wavelength and the frequency, and that is C is equal to the wavelength times the frequency. C is the speed of light, and 2.9979, I think, times 10 to the 8 meters per second. And again, that's a constant. A lot of people will use it as 3 times 10 to the 8, but again, I think they want you to remember that number there. The wavelength here, again, is usually in units of meters in this case. The frequency is in reciprocal seconds, and that matches the units here for the speed of light, which is meters per second. So it's important when you go into this equation that you do get your wavelength into meters. Very commonly, they may be in meters, but very commonly nanometers, again, is a sort of unit that is commonly used for waves in terms of their length. So nano being 10 to the minus 9, so you just do that conversion there as well. We could rearrange this and really solve for either one. So if you know the frequency or the wavelength, you could solve for the opposite, and it's really the same calculation, regardless sort of which one that you know. You basically take the speed of light and divide it by either the frequency or the wavelength, and obviously that will give you the opposite sort of value that is there. There is a relationship that we also talked about, which is in terms of wavelength. So if we have a small wavelength that usually revolves in a higher frequency, and that usually results in higher energy. And again, that's because it's pretty much just kind of repeating very, very quickly and kind of moving. If we have a longer wavelength, we usually have a lower frequency, and that usually results in lower energy. And that's like the one above there, where it's just kind of sauntering through space kind of slowly as it kind of moves from one point to the next. Now, in the relationships where we're sort of talking about in this chapter is, again, as those electrons sort of transition and that energy comes off, for example, from the atom, and it emits that energy, that may fall somewhere on the electromagnetic spectrum that we saw at the end there. The electromagnetic spectrum is the different sort of parts of electromagnetic radiation, things like radio waves, microwaves, infrared. The visible part of the spectrum, again, is where we see color. So that's where we see the red, orange, yellow, green. X-rays, gamma rays. And if we look at that chart again, as you got to the smaller wavelength, much higher and higher in energy. So things like X-rays, gamma rays are really high in energy because they have a really small wavelength. Things like radio waves, not so high in energy as they have a longer wavelength associated with it. So not all transitions of electrons will result in necessarily colors being seen. But if that wavelength of energy that's coming off in terms of that photon does correspond to that visible part of the spectrum, again, we will see some type of color come off. As we talked about, I think last time as well, that's sort of the idea there behind fireworks. Again, it kind of explode those fireworks, creates a lot of energy for those elements that are there, excites all those electrons, and again, as they're sort of coming back down, it will give off, colors that we see in the sky. Any questions on any of that stuff there? Okay, so the next thing, or continuing on this conversation, is sort of the idea of energy. And atoms, as we talked about, can emit or absorb only energy in discrete multiples. So remember that this is sort of the other idea that we talked about, which is the idea of quantized energy. And what it essentially means is, again, electrons, for example, will either gain or lose enough energy to sort of fully transition from one energy level to the next. They'll never find themselves, again, sort of halfway between. So they're either fully kind of go from one to the next, either upwards or downwards as well. And again, as I may drew before, and we'll see a picture, I think, in a second, you could think of quantized energy again like walking stairs. We can go from step to step. Usually, we don't usually stop in between. And that's sort of the idea of how electrons transition from different energy levels. So Planck gave this term a quantum of energy, which is the smallest amount of energy that's either emitted or absorbed into terms of electromagnetic radiation as these electrons are moving. You could actually calculate this by taking the energy here is equal to h times the frequency. H is what is known as Planck's constant, and it's 6.63 times 10 to the minus 34 joules times seconds are the units. Joules is obviously a unit of energy, and seconds is obviously time. Here, this is the frequency here. So in terms of these units, we have, bless you, joules times seconds, times 1/2. So the seconds cancel. And when you do use this calculation here, you will end up with units of joules when it's all said and done, when you do calculate that energy. Now, this is the formula that you can use to figure out the energy associated with a wave of light that is coming off as, again, electrons transition. This equation, along with, again, our previous one that we had, can be tied together because we could solve for the frequency is c divided by the wavelength. And that means when we take E is equal to h times the frequency, we basically can put that in and give us E is equal to hc divided by the frequency. H and C is both constants, which means that essentially if you just know the wavelength, you could actually figure out the energy associated with that. And obviously, if you know the frequency, you could just plug it into the original version of that equation. Once again, when you do go into this equation with the energy, the wavelength still needs to be in meters for everything to properly cancel out. So, and that's still based off of our speed of light here, which is meters per second. So this guy needs to be in meters. This is joules times seconds. So the seconds will cancel. The meters will cancel, and again, leave you joules when it's all said and done. So really important. Pretty much any of these sort of wave-like formulas, if you have to use the wavelength and you have to put them into the equation, you should usually put them into meters, and that will make sure everything sort of cancels out correctly. Any questions on that there? Obviously, I think as you continue on, they do want you to know Planck's constant as a value as you continue. So we'll go with you should know Planck's constant as well. Any questions? All right, so why don't we try one? What is the energy associated with a wave that has a wavelength of 465 nanometers? Once again, nano is 10 to the minus 9, which is also something you should know for sure. All right, give it a calc. Okay, so let's take a look. So we're looking for the energy. So that is our energy is equal to h times our frequency, which again, tying together our other equation into this one gives us hc over the wavelength. Clearly, we would want to use probably this version of it here since it has wavelength, and that's pretty much all that we're given. Once again, though, we do need to get this into meters, and this is in nanometers. So a reminder that what that would mean, our prefix here, and one of the prefix, there would be 10 to the minus 9 of the base unit, which is meters. So again, you want to make sure you don't kind of reverse that, which is a common mistake that people make. So we'll convert our wavelength from 465 nanometers into meters, so it's in the right unit. So 1 nanometer is 10 to the minus 9 meters. Those guys will cancel. Remember, that also is on your calculator if you have to punch it in. 1 times 10 to the minus 9, punch it in sort of as an exponent. That's going to give us 4.65 times 10 to the minus 7 meters. Now, C again is a constant, 2.9979 times 10 to the 8 meters per second. H is also a constant, which is Planck's constant, 6.63 times 10 to the minus 34 joules seconds. So now we pretty much have everything that we need to go into this equation, and that would give us our energy is equal to our Planck's constant times our speed of light divided by our wavelength, which has been converted into meters. Once again, here meters will cancel, seconds will cancel. That's going to leave us joules as our last unit standing, and that will get us 6.63 to the minus 34 times 2.9979 to the 8 divided by 4.65 to the minus 7. Going to get us 4.27 times 10 to the minus 19 joules is the unit, our energy associated with a wave that has that wavelength. Any questions on that calculation there? Okay. So let us then look at another one here. Let's see. Get super zoom. Try that again. All right, what is the energy associated with a wave that has a frequency of 2.87 times 10 to the 14 reciprocal seconds, which again is also referred to as a hertz? Okay, so on this one, we are looking for energy. So h times our frequency. In this case, we are given the frequency, which means we're pretty much good to go into our equation. As once again, h is Planck's constant, which is a value you always have. And you do need to know. So 34 joule seconds. So really on this one, I could just plug it in. 6.63 times 10 to the minus 34 joules times seconds. Times our 2.87 times 10 to the 14 reciprocal seconds. That's basically 1 over seconds, which means our seconds here will cancel, and that will leave us with joules when it's all said and done. And we will have 6.63 to the minus 34 times 2.87 to the 14. Gonna get us here 1.90 times 10 to the minus 19 joules in this case. Question on that one there. Question on how to calculate wavelength, frequency, energy associated with our photons. So again, they do want you to sort of memorize and know the speed of light. So make sure you know that, and also Planck's constant as well. Any questions on any of that? All right, then let's continue on talking about sort of our electrons and what is happening as, again, they're sort of transitioning. As we talked about before, again, an excited, for example, here, lithium atom will want to sort of lower itself back down in energy. And again, that's going to give off a photon of light to do that. That is what is sometimes referred to as an emission. And when we see something like red, and we can look at it through, say, a prism and a spectroscope, that's what is referred to as an emission spectrum, as these sort of electrons are transitioning back down, giving off that energy. The atom is releasing it, and it will release these colors, which is referred to as, again, an emission spectrum. An absorption spectrum is the opposite, is basically kind of when the atom gains the energy and those electrons kind of go upwards. So usually we look at an emission spectrum as these electrons are sort of going from higher energies to lower energies. So this brings up the idea of Bohr's theory of the hydrogen atom, which we'll talk a little bit about as we go through here. But one of the ideas is electrons do these transitions of these different energy levels. And as they do so, they will emit energy in the form of a photon of light. And that will also obviously give us some type of colors that we can see, like we see like in the flame test, or even when we look at like by a spectroscope. And we could do this by really adding energy to the atom. You could either do that by some type of, for example, like when we did the flame test, again, putting that energy in is going to excite everybody as it gains a lot of energy really, really quickly. Electrical discharge tube, when you run electrical current through it, will also do that as well. Maybe you've seen those before, like little neon tubes and stuff like that. That will excite these atoms in the gas phase by running really that electrical current through it. Now, a couple of things, when we see something, for example, like an iron bar that's really red hot, that's been removed from a high temperature source, it will glow. That visible part is the portion where we can again see with our eye. But we also feel other things like warmth coming off of it and stuff like that, which is in another part of that electromagnetic spectrum, which is the infrared spectrum region of it. So again, not all sort of transitions as the atom is sort of releasing the energy in the form of photons will correspond to colors of light that we see. Again, it may be fall somewhere else along that electromagnetic spectrum. A common feature of the emission spectrum of the sun and heated solids is that they are continuous, and all wavelengths of light are represented in the spectrum. So before we were talking about sort of electrons traveling from one energy level to the next in a sort of a quantized sort of version. A continuous spectrum, you could also kind of relate that to, instead of walking upstairs, for example, you walk up like a ramp, and on a ramp you pretty much can lay up anywhere along the way without falling. And that's sort of like a continuous spectrum, sort of everything sort of coming off at once, as opposed to the more quantized way that electrons transition, which is they're either on this step or that step or the next step, which are the different sort of energy levels. So when we talk about a continuous spectrum, kind of all the wavelengths of light are represented in the spectrum because you all sort of coming off at once. And again, that's kind of like walking up a ramp versus sort of the stair approach that we see in a quantized sort of situation. Now, when we do have an emission spectrum of atoms, like you saw with your flame test, and also like you could look at it through what's referred to sometimes as a spectroscope. The prism will separate out the light to its distinct wavelengths. We do see a couple of different types of spectrum, but we do see a very distinct type of spectrum that happens when we look at atoms in the gas phase. They don't show really that whole kind of rainbow of everything coming off at once. They have a more spectrum that's referred to as a line spectrum, and it is pretty much what it sounds like. You will see distinct lines that occur at specific wavelengths, and they will have specific colors. So, and they do correspond to those electrons transitioning from different energy levels. Each of the lines represents a specific wavelength, which represents a specific amount of energy associated with it as it's transitioning from one energy level to the next. It is so specific for atoms in the gas phase that by looking at the particular line spectrum for a particular element, you can pretty much know what it is based on the colors that you see, what wavelengths come off in terms of the line. So they're very, very specific for each of the atoms, and they're quite different. And experiments that you sometimes will do is that you'll have like an unknown, and you'll look at like a bunch of knowns and record sort of all the wavelengths of the knowns, and you could really figure out what your unknown one is based on the lines that you see. Every element will have that unique line spectrum, and this is sort of the experiment here that you could do it. You could have a light source and it goes through a prism, and again it will separate it out in colors. I think that might do something, maybe not. There you go. So there's our hydrogen lamp, for example. As we're exciting the hydrogen gas and looking through a slit as it goes through a prism, we will see these distinct lines coming out at distinct colors that correspond to pretty much our electrons transitioning. So we also talked about earlier as well that the colors itself have different energy associated with it. Red being a little bit lower in energy, and kind of the purple side there, or violet side, being higher in energy. So again, when we see something like a line over here, that would represent a much higher energy than we do over here at this orangey red sort of line at that end. And that would result in electrons perhaps not transitioning as far on the orange sort of line. So maybe it's just going down one energy level versus the violet one, where maybe it's traveling down several energy levels, which would require a larger amount of energy to be basically given off. Sort of experiment is sometimes done to do that. And you can use was, again, sometimes referred to as spectroscope, where you kind of look through it and you'll be able to see it. So these are the four distinct lines that we see in the hydrogen atom when it is emitting these photons of light. And again, each of those represent basically a transition of an electron from one energy level to the next. And this brings up the idea of the Bohr model of the atom. And the Bohr model of the atom is pretty complicated, but we're not going to delve too far into it other than just to talk in general about it, which is his idea really of the atom was this more planetary model of the atom, where you have your nucleus sort of in the middle, and then you have these orbits. And within these orbits, the electrons are basically moving around in nice pretty circles around the nucleus. As we will later talk about here in this chapter, and as we maybe talked about previously as well, electrons really don't sort of travel in this fashion around the nucleus. They actually travel pretty randomly about the nucleus. But his model was this more planetary model where, again, these electrons are moving around, where, you know, frankly, you can kind of put your finger on the orbit and know it's going to come around the circle and kind of get there. And in reality, it really doesn't travel that way. So it is correct in some cases, but it really doesn't hold up very well past hydrogen, which unfortunately has, you know, one electron. So as you get into things that have multiple electrons, his theory doesn't really work very well. But it does really explain, in terms of hydrogen, those four lines that we just saw in that spectrum, and sort of accounts for those lines that we see. And Bohr's model had some restrictions, which was a electron can only be located in certain orbits. So again, as those electrons are here, they will either be in this orbit moving around, or maybe they would transition to this orbit and moving around. And each orbit has a particular energy associated with it. And this energy is energy levels is what's sometimes referred to as n is equal to 1. That is the energy level. That really is what is known as the principal quantum number. And n equals 1 is the ground state, and that is the closest to the nucleus. So this would, for example, be n equals 1. This would be n equals 2, n equals 3, 4, 5, 6, 7, as you keep putting more rings on it. Anything above n equals 1 is considered basically an excited state, higher in energy, further away from the nucleus. And orbits, our electrons are fixed in these orbits, and they can only move from one energy level to the next. So again, if we did have an electron out here on the second energy level, it would have to lose a certain amount of energy to make it all the way down to the next energy level below it. And that would be quantized energy, like that equation that we just talked about. That energy is equal to h times the frequency, or hc, divided by the wavelength. Once again, they will not find themselves in between orbits or anything like that. So once again, this sort of quantized idea that the electrons would fully transfer from one orbit to the next is the idea here. And depending on how far these electrons are transitioning, again, would result in a different amount of energy coming off in terms of those photons of light. And that would correspond to the different colors that we see in the different wavelengths of light that came off for the hydrogen spectrum. So the emission of radiation by energized hydrogen could then be explained as really an electron dropping from a higher orbit to a lower orbit and giving off that photon of light, again here in this case, maybe red coming off as a result of that transition of one energy level. So those energy levels, as I mentioned a second ago, are what are referred to as principal quantum number, which is what the N stands for. That is the principal quantum number. As you take 1A, you'll learn about the other quantum numbers. There's 4 quantum numbers. There's N, L, M sub L, and M sub S. And the 4 sort of quantum numbers, as you'll learn in the next class, is basically the basis for electron configuration, where how electrons get into what orbits and what energy level they are on. But the basic sort of definition of N, which is the principal quantum number, is really just like the energy levels. So N could have values of 1 through 7. And really, again, as I mentioned earlier there, the N equals 1 is the ground state sort of closest to the nucleus. Anything above that's considered an excited state and would be further away from the nucleus, a little higher in energy. So the idea of Bohr's model is we have these electrons in these orbits and they're moving around in these nice pretty circles. And as they sort of gain energy and lose energy, they will hop from one orbit to the next. And to do that, again, there's going to be an exchange of energy that's going to happen from the atom. And again, if they're dropping from a higher energy to a lower energy orbit, the atom will emit and give off that amount of energy, which would be like an exothermic sort of process as it's releasing the energy. And if it is absorbing energy, the electron will go from a lower energy to a higher energy level. And that again would be a more endothermic process for the atom. Again, much like what happens when you stick it into the flame, it absorbs all that energy from the flame. And also when you throw the switch on the electrical discharge tube and turn the light on, it gains all that energy. Any questions on that there? So here we could see a couple of things. Once again, we have an electron transitioning downwards, emitting red light, as opposed to this one, which obviously had to travel a much greater distance through much more energy levels. And that's going to give us, again, a wavelength that corresponds to blue. And we would expect that because blue would have, again, a smaller wavelength than red and would require more energy to be given off for it or associated with it. So again, that makes sense as we were talking about before. So what we see, those 4 lines, is a result of each of these transitions. And again, you can see some of these here are not very far transitions, and some are a much longer sort of transition of different energy levels. And again, that's going to correspond to those wavelengths that we see. Longer wavelengths for our shorter transitions, and smaller wavelengths for our longer transitions, which require more energy to do so. So again, what we see with electrons and atoms is this more discrete here, quantized version of energy where we have only areas where it can lay up. Again, a continuous sort of version of energy like in the sun. Again, that electron could essentially lay up anywhere along the way, along that path there. So there's not a distinct amount. We always know, for example, if this is like our N equals 3 and this is our, say, N equals 2, there's only a certain amount of energy required to do that, and that electron will gain or lose that amount of energy to fully make that transition. Once again, it won't stop anywhere in between. And there's our stairs and our sort of ramp explanation as we talked about previously. So let's talk a little about the wave mechanical model, which is this idea that although Bohr's model of the atom worked really well to describe those kind of four lines that we did see within the hydrogen atom, it really doesn't hold up very well sort of past that. And there's a lot of experiments that sort of led to the idea of moving away from Bohr's model of the atom. So there's a lot of stuff that was done and a lot of ideas that sort of moved away from Bohr's model of these orbits. And one of the first sort of things are experiments that helped us sort of think about moving away from it was this idea of the dual nature of an electron. So in Bohr's model, the atom, the electron was restricted to only certain orbits at fixed distances from the nucleus. So for a lot of decades, people really didn't have any answer for like, why is it behaving like a wave? And a guy by the name of de Broglie sort of came up with this idea. And it actually was just an idea. He actually didn't do any experiments. He just sort of theoretically thought about it. And later on, it was sort of proven through experimentation. But he reasoned that light waves could behave like a stream of particles. Then perhaps particles could also possess a wave-like property. And according to de Broglie, he thought of an electron as being bound to the nucleus like a standing wave. So what does that mean? It means that obviously we know that electrons are negatively charged. So they're going to have an attractive force to the nucleus, which is positively charged. So although, you know, they are away from the nucleus, they're still sort of tied to the nucleus because of that attractive force. So they just can't fly away, right? So there is that some type of attraction. Even electrons furthest away from the nucleus will still feel some type of attraction to the nucleus, not as strong as closer ones, but they will still feel that attraction. So he thought that they would actually be sort of moving around like a standing wave. So like when you pluck a guitar string, right? The string is attached to the guitar, right? And as you pluck it, you get a wave that basically happens there in a standing position. It's not going anywhere because it's kind of affixed to the guitar. And the same idea here. So as the electron is traveling around, it is sort of traveling around as a standing sort of wave. And it is sort of affixed to the atom through its attractive force to the nucleus. So it can carry wave-like function, just like other particles and a wave will do itself. So this was the idea of the dual nature, as we talked about earlier, of waves and particles basically having properties that are very similar to each other as well, or carry over similar properties. So when we do have a wave, there are certain points which are referred to as nodes, which have no amplitude. So again, that's the part, if you have this sort of wave, that's really the part where there's really no amplitude, kind of the 0 point there. So he led to this conclusion that waves can behave like particles and particles can behave like wave properties. So when we think about these particles, we're moving away from the idea of electrons traveling these nice, pretty orbits, like little particles moving around nicely in circles. This idea that they're sort of randomly sort of about and moving about like waves from the nucleus. Another really important sort of move away from Bohr's model of the atom was one done by Heisenberg. And he came up with the Heisenberg uncertainty principle, which basically states that it's impossible to know simultaneously how a particle, and an electron is a particle, so a particle like an electron, where it is at any given time, and more impossible to sort of know exactly how it's moving. So the more that you know about its actual position, the less you know about how it's actually moving, and vice versa. So that is the uncertainty principle, which means that based on Heisenberg's idea, we definitely cannot have electrons moving in these nice pretty orbits, because if they are moving in circular orbits, like I said before, theoretically you could put your finger right there and eventually it's going to come back around the turn and hit your finger, right? if you could put your finger there, I suppose. But an idea there, you know for sure how it's traveling if it's in these sort of prearranged orbits like it was in Bohr's model. So this idea of Heisenberg, where we really don't know how any type of particle is moving, how fast it's moving, the position of it. And again, as we know more about one part of that, we know less about the other. So it would be sort of a little bit impossible for electrons to be in these kind of fixed orbits where they're just kind of circling around, because that would be in opposition to Heisenberg's uncertainty principle of you don't know how it's actually moving or where it's at any given point in time. Along with Heisenberg's uncertainty principle and de Broglie, how we sort of move away from Bohr's model of the hydrogen atom is with Schrodinger's equations, which we definitely will not go deep into. If you ever take physical chemistry, you got like a whole semester of like that's all you play with is those things, calculus and all those type of derivatives. But the idea of Schrodinger's equation is, based on Heisenberg, that we don't really know how things are traveling like particles. The best that we could really do is come up with, there's a very good probability of you could find an electron in a particular location within the atom. So we go from Bohr's model, where I know it's in this orbit, and again, if I put my finger there, it's going to come around the circle, and I know exactly, where the electron is traveling, to this more wave mechanical model, which is we really don't know exactly how particles like electrons are moving about the nucleus. We know that they are tied to the nucleus as per de Broglie's idea. We know that they can have wave-like function. And the best that we could do is go, well, there's a pretty good probability that in this area of the atom, we would find an electron. We have no real idea of how it got there, when it's there, how it's moving. But, if we had to lay some money down on a bet, there's a pretty good probability that maybe we'd find an electron there, as opposed to way atom where there's maybe a less of a probability of finding it. So what we do as we move away from Bohr's model is we really get rid of the idea of these nice, pretty orbits of where electrons are traveling to this idea of what are referred to as orbitals or atomic orbitals. And atomic orbitals, as we'll talk about, are really theoretical probability maps of where you can find electrons in an atom. And as we'll talk about in some slides here coming up, there are different types of orbitals. There's s orbitals, there's p orbitals, there's d orbitals, and there are f orbitals. And these are all the atomic orbitals, which again are really these sort of probability maps of regions where there are pretty good probability of finding an electron within an atom. We clearly know, as you just think about it logically, we obviously have our nucleus in the middle. So I would say that, again, there should be a relatively high probability of finding electrons near the nucleus. And again, though, as you sort of fan out further away from the nucleus, the probability, again, of finding electrons there will decrease. Not that you could not find an electron out there in that empty space, but there's a greater chance, right, of sort of finding it closer to the nucleus at a lower energy level than, say, at a higher energy level. Any questions on that there? All right, so let's take a look at one. This is sort of a probability map, and you can kind of see the difference in color. And the darker regions here are higher probability of finding electrons. And you can kind of imagine the nucleus there in the center. So again, that makes sense that, it's pretty dark around that center point. And as you can see, as you sort of fan out for where you would assume the nucleus is, you start to get some lighter color, which would indicate a lower probability of finding electrons in that area. Yeah. Yeah, so in general, these theoretical sort of maps, like these orbitals, basically the S, the P, the D, F, all elements basically share similar ones of that. The higher probability can't come with the idea of a couple of things. Obviously, if you have more protons in the nucleus, right, you're gonna have a greater sort of pull on any electrons. So that would make, you know, some higher probability being closer to the nucleus. But these are also separated, as we'll talk about, by different energy levels. So on certain energy levels, there's only certain types of orbitals that are available, and it is dependent on how many electrons you have and sort of where you're at and what orbitals they end up in. Yeah. But they all basically share the same type of atomic orbitals and stuff. Other questions? So let's talk about each of these atomic orbitals and sort of what they look like and what we have. When we talk about atomic orbitals, orbitals are, again, basically where we find electrons within the atom. And one really important rule is if this individual line here represents an atomic orbital, you can only put a maximum, and if each of these lines represent electrons, you can only put a maximum of 2 electrons within any individual orbital that you have, regardless of energy level, what type of orbital it is, S, P, D, F, it doesn't really matter. You could only really max out 2 electrons within a particular orbital. So that's important to sort of keep in mind. So let's take a look at each of these here. We'll start with the s orbital. The s orbital is merely a sphere, and s orbitals begin at the n equals 1 level. So the first energy level, the only orbital that you will find on that first energy level, which is the one closest to the nucleus, is an s orbital. And it was referred to sometimes as a 1s orbital, the 1 meaning it's on the first energy level, and the s meaning it's an s orbital, basically. There's only, no matter what energy level you are on, there's only one type of s orbital, which means if you max out the s orbital, you could put a maximum of 2 electrons, right? So maximum 2 electrons can fill that s orbital, then it's full. So when we think about these energy levels, n equals 1, the only thing that you're going to find on that level is just that 1s orbital. They're also on every other orbital as well. So if you went to the second energy level, you would find a 2s orbital. If you went to the third energy level, you would find a 3s orbital, and so on as you continue up away from the nucleus there. So S's start on the first energy level. They're found on all energy levels. Their shape is merely a sphere, as you can see here. That is what an s orbital looks like. It's a spherical shape with the nucleus at the center. So again, in the center, pretty much all these orbitals is sort of where you can imagine the nucleus is. And again, that will have really that high probability of finding an electron. So that earlier density map that we were looking at is sort of like an s orbital density map. And again, as we sort of feather out, it will get less and less of probability. What happens to distinguish between an s orbital on the first energy level, second, third, and fourth is as it goes up in energy, the size of the s orbital gets larger. So it just gets a bigger sort of circle as you continue upwards. And again, that's to accommodate all the extra electrons as you continue upwards in terms of the energy level to accommodate them. And that's what we see here. You can see this is a 1s, smaller 2s, and 3s, again, to encompass the more electrons that are present if you get to the third energy level. So they just sort of increase with size. So you do need to know the s orbital sphere. You also need to know that if you max out the s orbital, you could put 2 electrons in it. So this guy here could technically hold 2 electrons. This guy could hold 2 electrons. And this particular s orbital could hold 2 electrons on each of the energy levels. The next type of orbitals that we come across, they actually begin on the second energy level, and they are what are referred to as p orbitals. So p orbitals do not appear on the first, but the first appearance of them happens on that second energy level, and they appear afterwards as well on the third, fourth, fifth, and so forth. So p orbitals start on the second energy level. Unlike s orbitals, there's actually 3 different types of p orbitals. So there's 3 different types of p orbitals. there is a px orbital, a py orbital, and a pz orbital. And as we'll see there in that picture, they essentially are kind of like figure eights, if you will. They look like that. The x, y, and z is like the coordinate plane there in math, right? If there's an x, y, and z axis in three-dimensional space, so you got one on each of those in three-dimensional space. Now, because there technically is three different p orbitals, each one could hold a maximum of 2 electrons, which means if you filled up all the p orbitals on an energy level, you can max out with 6 electrons in what is referred to as the p subshell, or some people call it a sublevel. So what is a subshell or sublevel? It is all 3 of the individual p orbitals together on a particular energy level. So when we think about what's happening here in terms of our orbitals on our n is equal to 1, all we have is a 1s orbital, which is the s orbital on the first energy level. On the second energy level, we have a 2s orbital, and this is where we start to see what is referred to as our 2p subshell happening. Each of those lines representing one of the p orbitals, the px, the py, and the pz orbital. Any questions on that there? So taking a look here, look at that.
The 2px orbital is in the shape of a figure 8 along the x-axis.
And then our 2py is on the y.
The 2py orbital is in the shape of a figure 8 along the y-axis.
So again, you can kind of envision in the middle there, between the 2 lobes is where the nucleus is. So you could kind of vision as your nucleus or your node, as de Broglie was talking about, kind of a standing wave. And then most of our electron density kind of found again near that nucleus in those 2 lobes, where high probability of finding electrons are. And obviously RZ here is the same, just obviously on the other.
Orbital is in the shape of a figure 8 along the z-axis.
So as you can see here, this is our kind of higher probability of finding electrons as our nucleus is sort of envisioned there. Once again, a reminder that these are sort of based off of probability maps and calculations and stuff like that. Would you really see figure 8s and circles and stuff in an atom? Probably not, but it's just these sort of ideas of a probability of where you can find these electrons sort of housed within the atom in this wave mechanical model here. The next type of orbitals are actually what are referred to as d orbitals, and d orbitals do not start until you get to the 3rd energy level. And there's actually 5 different d orbitals. So there's actually 5. And as you can see down here is a picture of each of those. And since there are technically 5 different d orbitals, each one of these can hold 2 electrons. And that means that if you fill up the d, what is referred to as the d subshell or sublevel, you can max out at 10 electrons, right? So you can kind of see from these pictures here that the d orbitals kind of look like 2 p orbitals together. And the last one kind of looks like a p orbital through a donut at the end there. Again, these are the probability maps. And just like sort of our p orbitals, a lot of the probability of finding electrons are in these lobes, kind of very much near the nucleus, is a good high probability of finding those things. So kind of adding to our picture, on our first energy level, we had our, on our second energy level, we had our 2s, and that is where we first start 2p. And on our 3rd energy level, we have our 3s, our 3p, and that is where we start to see our 3d orbitals start to sort of develop. As we'll talk about, electrons will enter the atom really lowest energy and then kind of continue their way up in terms of energy as to how they are filled into the atom. Any questions on that there? And there's our D.
X squared minus y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
So again, in this case, we actually have kind of 4 lobes of probability of where electrons could be housed.
The 3D
And they're all pretty
The
similar.
3D XY orbital has a cloverleaf shape that lies in the XY plane and bisects the X and Y axes. The 3D
There we go.
The 3DYZ orbital has a cloverleaf shape that lies in the YZ plane and bisects the Y and Z axes.
And this one looks like a
The
dot.
3DZ squared orbital is shaped like a PZ orbital with a donut of electron density around the center. It is aligned with the Z axis.
So again, each of these lobes are probability and pretty high density spots of where you could find that electron within the atom.
This
And there we go. Now, the last set of orbitals are F orbitals, and F orbitals do not begin until you get to the 4th energy level. So that is where they begin. And there are actually 7 different types of F orbitals, which means obviously each of these guys down here can hold 2 electrons. And you can kind of see they kind of look like a mixture of our d orbitals, a couple of those d orbitals together. But since you can have 7 of them and each one could hold 2, if you max out the F subshell, our sublevel, you will end up with 14 electrons if you max them out. So adding to our sort of chart here, once again, on that first energy level, we have a 1s orbital, second energy level, 2s, and our 2p, third energy level, 3s, 3p, 3d, and now when we get to our 4th energy level, we have a 4s, a 4p, a 4d, and I'm running out of room, so I'll just write the 4f here with their 7 dots. Imagine 7 of them all the way here. But that's where they start to sort of come into play. So as you can see, as we sort of build up and continue on to higher energy levels, we incorporate more of these orbitals and theoretical maps of where electrons can be found. For the most part, F is it in terms of orbitals. In theory, you can have more orbitals than F. They actually just go alphabetical after that. So like G and so forth. But for electron configuration, for what you see on the periodic table, F is pretty much where you're going to sort of end up in terms of your electron configuration. Any questions on these? So once again, this is sort of where in the atom we will find electrons housed. You could think of sort of energy levels as like, floors in like a hotel. And you could think of the orbitals as like the rooms, right? And, you could kind of think of like a subshell that has multiple rooms, like a suite, right? You go into the one room and then there's multiple rooms that you can kind of go into as well. All right, so let's talk a little about the energy of these orbitals. Guy there. And by the way, some other terminology, when we look at something like this is what is sometimes referred to as a level or a shell, and that would be the n equals 1. This is our n equals 2, and again, every orbital on that would be considered the level or the shell. Now, on the n equals 2, this is where we have This is an orbital because there's only one. But our P here, which has 3 of them, this again, what is referred to as a subshell or sub-level. So sometimes this terminology sort of throws people off when they're asked questions like, how many electrons can you put into a particular orbital or a subshell and stuff like that. So if we go back and kind of look at what I had here, for example, we'll go to this guy. We'll do this right here, this here. So for example, here, if I want to know the maximum number of electrons in the n equals 2 shell, our level, how many electrons maximum can I put into that level or shell? So the n equals 2 shell or level would encompass everything that is on that energy level, which means each of those could hold 2, which means you could do 2, 4, 6, and 8 electrons if you max it out there, right? If I wanted to know how many electrons in the 3p subshell are sublevel, how many electrons could I put in that one? The answer is 6, yeah. And the 3p subshell or sublevel is just those group of p orbitals on the 3rd energy level. And there are 3 of them, which means each one could hold 2, 4, and 6 electrons in there. How many electrons in a 3D orbital? How many would that be? What do you think? 10. So that would be close, but not correct, because in this case, the keyword here is orbital, right? And any orbital could only hold a maximum of 2 electrons, yeah? So we don't know in this case if we're talking about this orbital, that one, that one, that one, or that one. So the trick question is orbital, and sometimes people miss that one. It is 2 electrons here. If the question asks how many electrons in the 3D subshell, the answer then would be 10. Yeah. So if it said how many in the 3D subshell, now we're talking about all of those guys together, and then that would be 10. Question on any of those there? You clearly don't want to probably draw these lines and dots and try to figure out, how many electrons there are. So there is a quick way that you could calculate if all you wanted to know was how many electrons you could put in a shell or a level. And to do that, the maximum number is 2 times n squared. N is the principal quantum number. So for example, n equals 2. You actually square it first. So 2 squared is 4. 4 times 2 is 8. Yeah. So 2 squared times 2 gives you 8 electrons. We do our n equals 3. 3 squared times 2. So that is 9 times 2, which is 18 electrons, which means on the 3rd energy level, 2, 4, 6, 8, 10, 12, 14, 16, and 18. So if you want to know quickly how many electrons there would be on a particular energy level or shell, you basically just take the n number and square it and times it by 2, and I'll give you, that's really good for something like, n equals 6, right? You take 6 squared, which is 36 2, right? And gets you like 72-ish maybe or something like that. Electrons without having to like draw all the little dots and or lines and stuff like that. Any questions on that? All right, so when we look at the energy of these orbitals, And in the hydrogen atom, because there's really only one electron present, all the orbitals are equal in energy. So what we mean by that is if we look at it, everybody on the n equals 2 level, for example, those are equal in energy. Everybody on the n equals 3 level, they're all equal in energy. Everybody on n equals 4 is all equal in energy. And this is what it looks like in terms of the energy of the orbitals when we have just hydrogen. And because hydrogen only has one electron, there's not a lot of electron-electron interaction. When we get into atoms that have lots of electrons, they really want to be near each other? Not really, because they're negatively charged, right? So because of all the extra electrons present, all the extra negative charges, things start to sort of move around, and orbitals start to move around as well to sort of accommodate that and allow things to remain stable. So what happens is as we go past hydrogen, that is sort of how the orbitals end up. Instead of being nicely together, they actually change. And this is really important because it affects how electrons go into the atom. Electrons go into the atom, lowest energy level first. So they'll come down here and fill, and then go to the next lowest, and then go to the next lowest, and then continue on that pattern until all the electrons are filled. The main difference that happens because of the separation of orbitals based on energy is as it goes from the 3s to the 3p, the next lowest in energy is actually the 4s, and they will actually get electrons first, and then it will fill up the 3d. So that S will actually get electrons first because it's actually lower in energy as the electrons are being filled into the atom than the d orbitals. And that's where people sometimes mess up because they just write it in order. It kind of makes sense. You go like 3s and then 3p and then 3d. But in this case, actually the S squeezes in there because it's lower in energy. So electrons will actually go here when it gets there and then start filling up the d orbital. So there is a certain order of how electrons get into the atom, and this is the order, and this is something that you do need to know, along with what we talked about earlier, that you can max out in terms of electrons: 2 for the s orbital, for the p subshell 6, for the d subshell 10, and for the f subshell 14. And if you know this, you could pretty much write any type of electron configuration that you would need to do. I'll talk about how we use this here. We start always at the very top, and basically we just follow the arrows. And when we get to the end, we go back and follow the next arrow. And then we zigzag back and follow the next arrow and follow the next arrow. And as you can see, you go from 3p to 4s and zigzag back to 3d. So you just keep zigzagging back and forth until you fill up all the electrons that you need when you write electron configuration. So do you need to really memorize this? The answer is yes and no. You should know the order, but this is something that you could actually create for yourself very easily by really remembering 4 things that we just talked about. And the 4 things that you have to remember if you wanted to make this yourself is, on the first energy level, the only orbital that is there is the s, right? It's not until you get to the second energy level that you find the p orbital. Not until you get to the third energy level that you find the d orbital. Not until you get to the 4th energy level that you find the f orbital. Once you have that, you pretty much just put the numbers underneath it with the same letters. So you could just make this 2s, 3s, 4s, 5s, 6s, 7s. This is 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And now you basically just recreated that pretty quickly. So if you just remember those 4 things where each of those start, and then just fill in the numbers, now you have on your paper the correct order of how electrons basically go into the atom. Question on that there.